Welcome back to Introduction to Lens Design. We're going to continue on talking more about some of the paraxial properties of optical system and how we calculate information about our optical system. And what I want to start by talking about are two very special rays or specific rays that we use to help define our optical system, and they're referred to as the marginal ray and the chief ray. When we want to define the properties of our optical system to first order in the paraxial region, we only have to trace two rays through the system. And although it can be any two rays, we usually use two very specific and special rays that are called the marginal ray and the chief ray. Now, what do they do? The marginal ray is the ray that starts at the base of the object. So if you will, if we have an on-axis source or an object, it starts on the optical axis, leaves at an angle, at some slope, it crosses through the top of the pupil. Notice it says pupils, so in an idealized situation it will be at the top of the entrance pupil, the exit pupil, as well as the aperture stop. And since it was at the base or on the axis at the object, it will also be on the axis or at the base of the image. Part of the information we can get by tracing this particular ray is it allows us to readily locate all image planes. And in a complicated optical system, or even in a not so complex optical system, we may have more than one image. Anytime the marginal ray crosses the axis, we're locating an image. It also tells us about the effective focal length, because again, where the paraxial marginal ray crosses the optical axis in image space defines the paraxial or the effective focal length. It also helps us define the F number, which is effectively the ratio of the focal length to the aperture diameter, which is the diameter defined when this ray reached the top of the pupil. The other special ray is referred to as a chief ray. And the chief ray comes from the top of the object, the edge of your field. For a lot of what we're doing now, we're going to have simply an on-axis point source as our object. But the chief ray comes from the top of the object. It will cross the optical axis at all pupil locations. And it will be at the top or the bottom of all image locations. Because if we think about it, often the images we form through an optical system, the magnification is negative. That, in other words, the top, what was above the optical axis in object space, is below the optical axis in image space. Sometimes that's important. Other times it doesn't matter what the orientation of the image is. But again, at all pupils, the chief ray height will be 0. At all pupils, the marginal ray height is the pupil size. What we get with the chief ray is the location of the pupils. Did the chief ray cross the optical axis? If the answer is yes, there's a pupil located there. It helps us define the field of view because the chief ray is the maximum slope angle that can make it through our optical system. And again, it defines our image height. So these two rays, any two rays allow us to define our system. But these two rays allow us to understand a lot about the paraxial behavior of our system. Okay. So here is, again, this is one of the example lenses from ZMAX. This is the 28-degree double Gauss lens. I'm sure some of you have your ZMAX up and running already. Some of you probably already are using ZMAX a little bit. So if you want to open up these files and examine them at any point, please do so. But the chief ray, which is the ray right here, I have some off-axis, infinitely distant field point. Again, this was a 28-degree field lens, so I've got rays coming in at 14 degrees. Comes through, crosses the axis here, so this is the aperture stop, and then is at the edge, or the top in this case, of my image plane. Now here's my marginal ray, and again it started from on axis at an infinite distance. By the time it reaches the lens, it has the optical system, it has this height, crosses through the top of the aperture stop, and then crosses the optical axis at the image plane. Now, if we want to locate our entrance and exit pupils based upon the chief ray, again, it crosses the optical axis at pupil locations, what I can do is simply take a continuation of my chief ray from object space, so I'm going to ignore refraction and just come on through until the ray crosses the axis. That tells me where my pupil is located. It also tells me the size of my entrance pupil. Okay? I can also trace my ray back from image space and again do the continuation until it crosses the optical axis. Now, since this is a real system and it does have some aberrations, including what are referred to as pupil aberrations, I'm not exactly crossing the optical axis here, but I am defining for you where the exit pupil is. So the exit pupil is embedded in the optical system, and it's actually closer to object space than the aperture stop, and even closer to object space than the actual entrance pupil is itself. So let's talk a little bit about the F number or focal ratio. The entrance pupil has a size as well as a position. Okay, and we saw sort of that line segment in the previous graphic was showing both the size and the location of my entrance pupil. If I have an infinitely distant object, then I can define the F number, or focal ratio, as simply the paraxial effective focal length divided by the entrance pupil diameter. Okay? The problem is if I am not at infinite conjugates, then my image isn't formed at the paraxial focal point, and we saw that in some of the lectures from last week. Okay? So what we need to do in the cases when we're not at infinite conjugates is we have to have another way of defining this property. And we do it based on what's called the numerical aperture. And the numerical aperture is simply the index in this particular space, in this case object space, times the sign of the marginal ray in that space. Okay? So my F number in image space would be index in image space times the sign of the marginal ray in image space, and my F number is 1 over 2 times that quantity. In the limit of our system being at infinite conjugates, this equation works just fine. So this equation can be used in any situation, but you have to do a little bit of math. This calculation is pretty straightforward. Normally these are 2 defined system parameters, but it's only appropriate for objects that are at an infinite distance away when you're working at infinite conjugates. Another concept I'd like to talk about is what's called the Lagrange or the optical invariant. Many other names for this as well, but I'll stick to the Lagrange or maybe optical invariant for now. This invariant describes something that, of course, doesn't change, doesn't vary. It's a constant for an optical system. It tells us information about the light that propagates through an optical system. What's important about the Lagrange invariant is once you know what it is anywhere, and that could be at the object, it could be at the image, or it could be anywhere within the system, you know what it is everywhere, ignoring losses that occur in the system. And again, in the paraxial region, we're always ignoring these types of losses. The ability to use the Lagrange invariant or to calculate the Lagrange invariant is extremely useful in first-order optical design. You can use it to very quickly determine whether or not an optical system is even feasible. Now, where do we go with the Lagrange invariant? How do we calculate it? Let's start with our paraxial ray equations, but specifically for the marginal and the chief rays. And you'll notice I've got omega prime equals omega minus y phi and something similar. Classically, when we put a bar on top of the parameter, we're talking about the chief ray. If we don't have the bar on top, we're talking about the marginal ray. So here are the refraction of the marginal and chief rays, translation of the marginal and chief rays, and we can do a little bit of math, either using these two equations or these two equations, set them equal to each other appropriately. And this quantity, which is the chief ray height times the marginal ray angle minus the marginal ray height times the chief ray angle, in any space, so this would be an object space, this would be an image space, is equal to this Lagrange invariant. So with just a small revision, what we can say is once we calculate this at any location in our optical system, we can determine what it is at any other of the k spaces in our optical system. Okay? So given the input properties in terms of height and slope, height and angle, I can only specify one of the image properties. So if I want to have an image of a particular height, then the cone angle, the acceptance cone angle, again the numerical aperture if you will, is defined. Okay? If I want a smaller object, I'll have to have a larger numerical aperture. If I want a small numerical aperture, then I must accept a larger image. This is also referred to as the A omega product law that tells us that the product of the area and the angle is a constant as the light propagates through our optical system. And that's probably enough for this session, so I will continue on shortly. Thank you very much.